Greetings. This is Anthony Dick. This is a recording of a walkthrough for the regression practice test. I'm sorry, I already did number one because I thought I was recording and I started talking, but I wasn't. So number one, on May 11th, 50 randomly selected subjects had their systolic blood pressure recorded twice, first time at 9, second time at 2 in the afternoon. If one were to examine the relationship between the morning and afternoon readings, then one might expect the correlation to be. So thinking about if you take somebody's blood pressure in the morning and afternoon, they probably won't be that different, right? So the correlation would be near zeros. Morning and afternoon readings should be independent. They're not independent because a person with high blood pressure has high blood pressure. It's not variable. Well, I mean, anyway, your blood pressure doesn't magically change that much. So I wouldn't expect near zero. Now, I noticed that D and E said near zero. I really don't care why the readings is because I don't think it's near zero. So C said high and negative, as those with relatively high blood pressure in the morning will tend to have relatively low readings in the afternoon. Think, will a person's blood pressure change from morning to afternoon that much? No. I guess maybe unless they are alive in the morning and not so much in the afternoon. High and positive, yes, because if they're high in the morning, then I expect them to still be high in the afternoon. If they're low in the morning, I still expect them to be low in the afternoon. So I chose B. Okay, number 2. If bivariate data set A has correlation 0.95 and a second bivariate B has correlation negative 0.995, so I'm thinking ahead. That's a strong positive correlation. That's a strong negative correlation. A linear model does a better job at describing the relationship between variables in data set A than B. A linear model. Now, here's the deal. All this tells me is the relationship is strong and positive. The relationship is strong and negative. It does nothing to tell me about the linearity. Remember the hot chocolate? You can have an extremely high or extremely low correlation, negative or whatever correlation, and it might not be linear. So I'm looking, linear model does a better job of describing the relationship between variables A and B. I don't think that's true. Linear model does a better job of describing the relationship between variables in B than A. No, because it's talking about regression telling you about the linearity of the model. That doesn't happen. A linear model is the best description of the relationship between the variable in both data set. No, you can't tell whether either data set is best described by a linear model until you examine the scatter plots. A mistake has been made. R cannot be negative. That's stupid. It can be negative. D, there it is. Okay? Remember, the regression tells you the strength and the direction. It does not tell you about the form. To get the form, whether it's linear or not, you have two things. Right? You have the scatter plot itself or a residual plot. Those will tell you whether it's linear, not the regression value. Okay, let's look at number 3. A regression of the amount of calories in a serving of breakfast cereal versus the amount of fat gives the following results. Predicted calories. Remember, that predicted is important. Make sure it's there, or Y hat. Predicted calories equals 97.1053 plus 96.05 fat. Which of the following is false? It is estimated that for every additional gram of fat in the cereal, the number of calories increases by about 10. You see what that's trying to do? That's interpreting slope. I like that so far, but I'm going to read the rest. It is estimated in cereals with no fat, the total amount of calories would be about 97. That's describing the y-intercept. Oh, which one's false? So that's true and that's true. Because, okay, I'm getting confused. Like, both of those are true. Those are good answers. But it's which one's false. I got to read my question. If a cereal has 2 grams of fat, it's estimated the total number of calories is about 116. Well, if I put in 2 here, this is like about 10-ish, right? And if I put in 2, 2 times about 10-ish is about 20-ish, maybe a little bit short. If I had about 20-ish to 97-ish, that's about 116. So I think that's pretty darn good, especially when I look. This isn't quite 10. It's about half off. And if I put 2 in there, I'm pretty sure I'm going to, because I'm talking about it. 97.1053 plus 9.6525 times 2 gives me, 116.4-ish. That works. The correlation between the amount of fat and calories is positive. Yes, because the slope is positive. So that only leads this. So why is this false? If one cereal has 140 calories and 5 grams of fat, its residual is about 5 calories. Well, if I put 140, if I put 5 in there, so I'm going to put a 5 in there, I would predict this to be 145.36 is the prediction. And remember, the residual is the actual value minus the prediction. 145 gives me about -5. So that's not true. Its residual is actually about -5 calories because this actual value is 5 below the prediction. Okay, so there's E. E for excellent. A copy dealer has data on the number of copy machines X at each of 89 customer locations, number of service calls, a month Y at each location. Summary calculations give X equals 0.84, S of X equals 2.1, Y equals 14.2, S of Y equals 3.8, R equals 0.86. What is the slope of the least squares regression line of the number of service calls on number of copiers? Ooh, dang it. I don't have the formulas in front of me. So let me look it up real quick. But remember on your green sheets, we did one of these in class. You can tell, I don't remember, I believe that the formula for slope is R times S of Y over S of X. I'm pretty darn sure that's it. But you can tell I haven't memorized it because I don't need to. And actually, I just looked it up. That's what it is. So this is the kind of question that you might see involving that kind of problem. So my R value is 0.86. So I'm just going to type this into my calculator. 0.86 from right there. S of Y is 3.8 times 3.8 all over S sub X is 2.1, and I get that, which is 1.556, and there it is, B. Okay, now remember, I could calculate using that formula, and this is on your green sheets on the very front page. Okay, you do not need to memorize it. You do need to be aware that if you have the regression line, if you have the regression line and your averages of X and Y and all that jazz, you can find your A and B for the correlation for the regression line. I don't know if I just said what makes sense. I'm not making sense. I'm going to move on. Okay, number 5. Cool. Number 5. In the setting of the previous problem, what about the percent of variation in the number of service calls? You see this phrase? Percent. Excuse me, guys. Good morning. I haven't cleared my throat yet. Percent of variation in the number of service calls that is explained by the linear relationship between the number of service calls and the number of machines. You see that phrase? That's one of these things that I say you better dang well have stuck in your head. Tattoo it on your brain. This is the percent of variation in the output variable explained by the linear relationship or the linear regression between the input variable. That's your R squared, or your coefficient of determination. So all I got to do is I got to take my R value and square it. I have in my calculator right there, I have my R value, right? Squared. Bingo. And I get 0.7396, which is about 74%. Cool. Okay, guys, That phrase, it's going to show up either on a free response question asking you to interpret it, or it's going to show up in a multiple choice with that phrase in it. Guys, if you know that phrase, if it's tattooed in your brain and you recognize, oh, that's my R squared, that's an easy question. If you don't, then it's not going to be, you're not going to figure it out. Okay. A study examined the relationship between sepal length and sepal width for two variety. What's a sepal? So I'm curious now. Sepal. I think that's like the petal part of the flower, if I remember right from my AP Bio days. Sepal. No. I remember. The sepal's like the base. The base of, like, you have flower. There's that kind of green thing right there. I'm really sure that's called sepal, if I remember that from my AP Bio days. Okay. A study examined the relationship between sepal length and sepal width for two. But see, I got distracted. And on a timed test, that's a big deal. I don't care what it is, right? All I care is it's a relationship between the sepal length and sepal width for two varieties of an exotic tropical plant. Varieties X and O are represented by X's and O's. So there's X's and O's in the scatter plot. Which of the following statements is true? Considering variety X only, there is positive correlation between sepal length. No, negative correlation on both of them, right? Considering variety Y, the least squares regression line for predicting sepal length has a positive slope. Positive relationship? No. Positive, that's bad. Considering both varieties together, there is a negative correlation between. Actually, if I consider both of them together like this, actually, that's a positive relationship. See that? This is one of these cool scatter plots where if I consider it all together, it has a positive relationship, but as soon as I put a categorical variable into it, I can view them as one. So that's not right either. I changed my ink color. Considering each separately, there is a negative correlation between sepal length and width. That's true, but I'm going to read. Considering both varieties together, the least squares regression line for predicting sepal length has a negative. No, because that's saying the same thing as E. So that's bad too. So D, as in dipstick or dingo or Mr. Dick. Okay. 7. Suppose we fit a least squares regression line to a set of data. Which is true about the plot of the residual shows a curved pattern? So think, residuals show a curved pattern. You know it's not a linear thing. A straight line is not a good model for the data. That almost seems too easy. Correlation must be 0. No, we know that's not true. Remember hot chocolate? Correlation must be positive. No, it could be negative. All we know is there's a curve. Outliers may spread. I don't know that. The regression line might not be a good model for the data, depending on the extent of the curve. What's true? Might not be a good fit. No, it might be a pretty good fit. And this is something we didn't talk about in class, but remember the hot chocolate medal? For that data, that was actually a decent prediction. It was a little off, but a linear line wasn't a good model. Okay? Just because we cannot find a line doesn't mean the model's bad. It just means it's not the good one, not the best one. Depending on the extent of the curve. Might not be a good model depending on the extent of the curve. The regression line might or might not be a good model. No, and this is where it's wrong. Might or might not. No, it's not. There's no might or might not. It's not a good model. Okay? We could still use the model. It's just not a good model. A straight line is not a good model. True. 7. Okay. Number 8. Number 8. Let's look at number 8. Okay. Mr. Nerdly asked the students in the AP Stats class to report their overall GPA and their SAT math scores. The scatter plot below provides information about the student's data. The dark line is the least squares regression line for the data, and its equation is that. Okay, and I look at this. I see a moderately weak or moderately strong positive correlation with, do I see outliers? I don't know. These are far enough away that I don't know that there's any patterns out there. Okay, what's true about the circle point? The standard score for this GPA is positive. The standard score for this GPA is positive. Standard score for this GPA is, okay. The standard score for this GPA, let me come back to that one. If we use least squares regression like predicts AC, we would make a prediction that's too low. No, now that's not true, because the prediction would be up here, and our prediction would be too high. The standard score for this student is positive. The standard score for this student's GPA is positive. No, it's not. The standard score would be its z-score. That's what a standard score is. And I was thinking the standard score on here, this is obviously below the average, because the average is going to be up here closer to all these. Think about it. These are the only data points that are lower than that one or at the same. So it's the average z-score GPA is going to be up here. And so this is below it. So this is going to have a negative z-score. Z is going to be equal to a negative number. That's tricky. I had to think about that one. The student's residual is positive. No, it's negative. We already talked about that. B and C are doing the same thing. Removing the data point would change the correlation between SAT math scores and GPA. So if I took this out, would it change the correlation? Not really, because still, if there it is. It wouldn't change it that much. I mean, of course, anything's going to change it, but it's not going to change it that much because it's not influential. It doesn't. Remember how we put z-scores in and it really strengthened or really weakened it? That's not going to do either one. So I don't like that one, but I'm going to hold off on it. Removing this student's data point would decrease the slope. So if I got this, think of this point as pulling it. What would happen to that line? Well, that line would receive less of a pull. So the GPA is low and SAT is low. So that line is pulling it down. So it would kind of crank up like that. That goes from positive to less positive to negative, right? So I like this. That's it. Okay? Would not change the correlation. Now, it's not going to change the correlation too much at all. Is true. Removing this would not change the correlation. Okay, I'm really firm on E. Would not change the correlation. You take any point, and I was thinking, how much is it going to change the correlation? It's not going to change the correlation that much, I don't think, because it's still weak. But it will change the correlation. Period. The only way you take something off that will not change the correlation, no, that's because if it's right on there, it's going to be. Is there something you could pull off that wouldn't change the correlation? I don't think so. Interesting experiment, but would not change correlation. It will change the correlation. So there it is, E. 9. Sorry, guys. I'm taking too long on this. 9 to 9 to 9. One characteristic of roller coasters that contributes to the maximum speed of the ride is the track's max height. Below are computer outputs and a residual plot for the regression of maximum speed in miles per hour on maximum feet for 9 roller coasters that opened recently around the world. Okay, this is the residual plot. Okay. The circled point represents and now this is all the computer data. So predictor, coefficient, There's my height in feet. So there's my y-intercept. There's my slope. And I see an r squared value. And I could take the square root of that and get the correlation coefficient. And I could look at the slope is positive. So I'd take the positive of that. We're never going to use this adjusted y squared value. We will use these things eventually, but not today. This is the standard deviation of the residuals, or about how far apart the residuals are. If I took the all of these data points and I found the standard deviation of those distances, that would be it. Okay, the circle point represents a roller coaster in the Philippines, whose maximum height is 70 feet. The observed speed of this roller coaster is closest to... The observed speed of this is closer to, well, I see it's at about 12, right? 5, 10, maybe 12-ish. But that's wrong, because that's the residual. That's the distance above its prediction. So its prediction, I've got to actually set up my regression line. Y hat equals 28.174 plus 0.21435 times x. And if I put 70, into that regression line that I just got from here, I'll get my speed. So I go 28.174 plus 21435 times 70. I get 43.178. So equals 43.1785. That is my observed thing. So there it is right there, about 43-ish. I don't believe. Oh, no. Holy smokes, I just got sucked into that, didn't I? That's the prediction, right? This is 12 above the prediction. So if the prediction is 43 and I add 12 to that, I get 55. There we go. Okay. Wow. There's a lot of really good distractors in that question. Distractors are things that we get in the process of solving that are not the real answer. So the residual is 12. The prediction using the regression line, and I got the regression line from those two figures. This one that says constant, or this first number you see, is always the y-intercept. This second number is always the slope. Okay, so I set up my regression line. I got my prediction. I noticed this is 12 above the prediction, so I take the prediction plus 12 and I get 55. And there it is. Whoa, kind of like, wow, that's... Which of the following best represents what S equals 10.371 is in the setting? Oh, that's right there. Oh, sorry, I'm looking at 10. Now, I've already said what that is, and I apologize. We never talked about that in class. We were going to do that when we came back. But S is the standard deviation of the residuals. And the residuals, remember, is the observed minus the predicted. So I'm looking at this. It's the standard deviation. So look at A, B, and C. Standard deviation of the standard deviation of the... Oh, look at this. Standard deviation of the residuals. Bingo. Right there. Okay? That's all there is to it. Okay, cool. Moving on. Part 2, number 11. Because elderly people may have difficulty showing work, still standing to have their height measured, a study looking predicting overall height from knee height to knees. Here are data in centimeters for 5 elderly men. So knee height and their actual height, and these are all in centimeters. Which variable is explanatory? Which varies response? Well, their input, their explanatory, knee height, right? Because that's the one they're using to explain their height. Okay? Construct a scatter plot on your calculator and draw a rough sketch from your scattered layers display. So if I make a rough sketch in my scatter plot, I'm going to have my knee height down here and make sure we label. And I'm going to have my height up here. Now I'm not going to use my calculator for this. My smallest knee height is like 43. So if I go like from 40, 42, 44, 46. Oh, this is horrible. 48, 50, 52. I should have thought what I'm calculating. 54, 56, 58. And then smallest I've got height a 146 all the way up to 190. So I need to get like by 50. So I can go, if I start here at say 140 and then I go 50, 60, 70, 80, 90, 200. And you can just start off and get little things like that. Okay. Now, I've got 57.7, so that's about 58-ish and 192. So 58-ish and 192, that's like right here-ish. 47-ish and 153, so 47-ish is here, and 153 is right about there. Okay, 43.5, that's right about there, and 146, oh, that's kind of right, like right there-ish. Okay. 44.8 and 463, so 44.8, that's kind of right there, and 163, 50, 63, that's kind of there-ish, and 55.2, 169, 55.2, that's right there, and 150, 69, right about there-ish, right? Yeah. Okay, so I look at that, describe the form. Now, often you won't see this. They'll just say, describe the relationship that you see. That's where I'm looking for my stuff, right? Well, I'm looking for the strength. That seems to be pretty strong because they're all following this pattern. It's definitely a positive trend or a positive direction. There aren't really unusual features because these are all right in this pattern, right? And it looks pretty linear. So my final statement is that the relationship between knee height and height is strong, positive. So strength trends has no unusual points and appears linear. Now, I put that appear in there to give myself a little wiggle room in case it's like the hot chocolate where, yeah, maybe it's not really linear, but I don't see it. But it appears linear, definitely. Use your calculator to determine least squares regression line. Write the equation below. Now, guys, I'm not going to do that because I will never ask you on a test or anything else to find the regression line. I'm not going to do it. Okay? And the AP test will never ask you to do it. So I'm going to skip it. D. Suppose a sixth elderly man with a knee height of 57 and the height of 150 is added. What impact would have this on the correlation and the slope? I'm going to put this as a red point. and I'll put it in here so I can see it. 57 and 150. That's way over here. Whoa. Look at that. Look at that. Look at that. So previously, this was my line. That's going to pull that line down. So the slope is positive. It's going to be less positive. So it's going to decrease the slope, and it lies outside the pattern. That's going to weaken my correlation. So what would an effect have on the correlation? It would weaken R, period. And the slope, it would decrease the slope. Okay. Now this asks, should you use your regression line from part C to predict the height of an elderly man whose knee length height is 70 centimeters? If so, do it. If not, explain why not. I didn't even find it. But look, 70. Here's 58. 70 is way up here. Think what that's going to do. If I predicted it, that might be like way up there. No. Why not? Because this lies so far outside of my regression data that is likely to be a bad prediction. Guys, we call this extrapolation. And if I just put no, extrapolation, I'd be okay with that. No. The 70 centimeters is far outside my data. It would not be accurate. Would not be accurate. And if I'm trying to describe extrapolation, by dang well use the word extrapolation, because extrapolation has a very specific meaning. It's using predictions, making predictions outside the domain of your data, and it's generally a bad thing. Okay? I mean, you can do it, but the predictions are often not accurate. Okay, let's look at something else. Wow, these are only two problems here. Cool. Scientists studying outbreaks of locusts in Tanzania found a negative correlation between the amount of rainfall. So I start making notes here. And the relative abundance of red locusts. So number locusts, inches, rain, like that. So as there's more rain, the locusts go down. Okay. 18 months later. 18 months later. Okay. Relative abundance is measured scale 1 to 5, where 5 means okay. But okay, and so here's my least squares regression line. Okay, interpret the slope in the context of this problem. Well, the slope is right there. And this is for every additional. So think of this as a fraction, and this is the output is locusts. Locust, or your abundance scale, your relative abundance of locusts. So right is, okay, here's what I'm saying. Sorry, I'm rambling. Think of it as rise over run. The rise is describing your y variable. The run is describing your x variable. So for every additional rise, which is the abundance score, and the run is the x variable, the inches of rain. So for every additional inch of rain, the y variable, predicted relative abundance, will decrease, because it's negative, by 0.12. Okay, So for every additional, bingo, there's your input variable. The predicted output variable it's either going to be decrease or increase by something. Okay? This is kind of a fill in the blank. Okay? Well, not kind of, it is. Interpret the slope for every additional unit of input variable. The predicted output variable will increase or decrease by whatever the slope is, period. Okay, the correlation between these two things is negative 0.75. Well, that's pretty strong. If the amount of rainfall were measured in centimeters rather than inches, how would the correlation change? Explain. It would not. Okay, remember, correlation is not affected by units. Is not affected by units. Okay, correlation doesn't change if I switch my x and the y variables. The correlation would still be exactly the same. If I changed my units, it would be exactly the same. Correlation is strength, and the strength doesn't change if I change the scale down here. Okay, it might zoom out or but it doesn't change the strength of the relationship. Explain what the least squares means in terms of the variables involved. Wow, this is the least squares. This is kind of asking me to give a general interpretation of what that thing means. So the least squares, remember, minimizes the sum or the squares of the residuals there, right? So if in the context of that, in terms of the variables involved, okay, the least squares minimizes the square of the residuals. And if I put a residual, the residual is the predicted locus. I'm looking at my graph up here. The residual is the distance between the predicted locus or the predicted locus score and the actual locus score. So minimizes the square of the distance from the actual locus score. What do they call it? Relative abundance. Relative abundance score from the actual relative abundance one, and square of the distances from the squares of the distance from the relative abundance score and the predicted abundance score. So the least square line is the one that minimizes the distances, the squares of the distance. I guess technically it's the sum of the squares of the distance from the actual relative abundance scores. But if you get something minimizes the squares, if it minimizes the squares of the distance, it's by default going to minimize the sum. So I guess that's a little extra, but technically that's what it is. But yeah, minimizes the squares of the distance from the actual relative score. Okay. Would it be appropriate for scientists to conclude that changes in rainfall are responsible for, in other words, they cause the variations in the relative abundance of red locust region? Why or why not? No. Remember, I can only conclude one thing causes another if there is an experiment involved. This is an observational study. No, this was an observational study. Only an experiment can determine cause and effect. There's definitely an association. There's a very high correlation, but the only way you get to determine cause and effect is if you have an experiment. Okay, that's it, guys. Thanks.